Right, so in these two examples, we see two lots of similar triangles. The first similar triangle we can see is that here we have one smaller triangle inside a larger triangle. So that is the larger triangle, and the smaller triangle inside that, we see that these lines here are parallel. So if we look at triangle ADE, the smaller triangle, we can say that that is similar to the larger triangle, which is A. The corresponding angle to D would be B, and to E, C. The reason is that that is equiangular, or angle. So these similar triangles are convenient because we have these information already given to us, so we can work out this side BC using the ratio. BC in the larger triangle relates to the side length of 9, and the corresponding side here is 4, and the smaller side 3. So if we multiply both sides by 9, 4/3 times by 9, dividing by 3, we'd get BC being equal to 12. So we'll write that on the diagram. So now that we've got this side length here, we can use our other lot of similar triangles. We can see here the butterfly sorts of similarity here. These two blue triangles are also similar. And so if we're trying to work out x over y, these are the corresponding sides here because we have vertically opposite angles, and these alternate angles are equal, so it's between these two marked angles are the corresponding sides. So if we knew the corresponding side to 12, we'd be able to work out that ratio. So to do that, we're going to look at another triangle. Let's look at triangle DBF. And this is a special type of triangle. We know that because these are also alternate angles, let's use the same marking as this angle, that because these two base angles are equal, these sides must be equal. We have an isosceles triangle. So if that side is equal to 6, then we can safely say that this EF must be 2. And so from that we can say that since this triangle here, EFH, is similar to, now the matching angle is C, to F is B, H, the reason being that they have equal angles. And so we can see that x over y, in the smaller triangle x, so 2 would be 2, and in the corresponding side 12, and if we simplify that, that would be 1 over 6. So in the next example, we're using this same idea in a slightly different way. We can see our similar triangles, larger one, a smaller one inside the larger one. And so here we're looking at the scale factor. So here we're multiplying this out by 3. So if this length is x, then we can safely say that this length here would be 3x. And that means that this smaller length here must be 2x. And you can get that ratio if we consider the side lengths here. You could solve the proportion x over 2 equal to, now x plus y plus z would be plus y plus z would be the corresponding side over 6, and you'd get that eventually y plus z is equal to 2x at the end of that. I'll leave that as an exercise. So from here, if this proportion here is 2x, then now we're going to use our butterfly similarity here, because we know this information, DF is parallel to BC. So we have alternate angles and vertically opposite angles. So we see this ratio here is 1 to 2, so we're doubling the side length here. So this length would be, again, in the same sort of idea, be split up into 3 parts. So y we could think of as being 2x over 3, and z being, well, double that, 2 times 2x over 3. So when we go to do these ratios, x over y, well, x is x, but y we can think of in terms of x as 2x over 3. And if we multiply the numerator and denominator by 3, we get 3x over 2x, which is 3 over 2. So we can do the same thing here with y and z. Well, because these are parts, the corresponding sides of the blue similar triangles, we can use the information that's given on the side lengths here. So the corresponding side for y would be 3. The corresponding side in the triangle that has z would be 6, and so that ratio would be 1 to 2. Or you could use this this ratio we discussed earlier, also 1 to 2. X over z, so let's write z in terms of x, would be 4x over 3. Multiplying numerator and denominator by 3 would get 3x over 4x, and that simplifies to 3/4.